Hopefully people are continuing to sign up for demos. If you have not yet signed up for a demo, please do so. What I wanted to talk through today, last time, in last lecture, we talked about how to send and receive packets, UDP packets with the Pico W. With that ability to send and receive UDP packets, you unlock an interesting capability, which is the ability to communicate with a network time protocol server. So there exist these servers out there in the world with known IP addresses. If you are a network connected device and you send a packet of a specific format to one of these servers, it will respond with the time of day. And so that's a pretty handy capability to have, particularly if, for instance, you're making, I know that there's one group, for instance, making a little wearable watch as a final project out of a Pico W. So this ability implies the ability to connect your Pico W-based watch to a network. It'll send off a UDP packet to a network time protocol server. That server will respond with the time, and you can just update the time on your watch to the absolutely correct time, to within a millisecond or so, just by connecting to the network. I can imagine a pretty interesting arrangement for that, where perhaps occasionally the Pico W just looks for your phone's hotspot network, and in the event that it finds it, it connects to it, updates its time, and then goes off again, stops trying to connect again. So that if you wanted to make sure that the time on your watch was connected, you would just turn on your hotspot. It'd be kind of interesting. So I'd like to talk through that. The way that I would like to go about this, and I'll mention, by the way, that this also gives me an opportunity to talk about a peripheral that we have not yet talked about on the RP2040, which is the real-time clock. And so what I'd like to discuss is, first of all, how we can do a UDP transaction in order to acquire the time from one of these network time protocol servers, and then how we can use that time to update the Pico's real-time clock. The real-time clock, I'll just summarize. It's a peripheral. Let's see. Let me pull up the data sheet. Oops, I always do that. Hold on. Something happened to my screen. Cancel. OK. The real-time clock, if we look at this diagram, it is another one of these peripherals. It's labeled RTC here. You may remember from our discussion, a couple months ago at this point, one of our first discussions about an external peripheral was about the timer. And you may recall that that's a microsecond timer. It increments once per microsecond. And we can associate alarms with that timer, but those alarms only see the lower 32 bits of that 64-bit incrementing timer. So the full 64 bits overflows in, like, I forget it, some crazy number of hundreds of thousands of years. But how many? 600,000 years. But the lower 32 bits that are actually visible to your alarm infrastructure, those overflow on the order of like 72 minutes, which implies that if you're trying to measure time beyond 72 minutes or schedule execution of code beyond 72 minutes, you need some other mechanism of keeping track of time. That other mechanism is this real-time clock. The real-time clock is a peripheral that allows for you to specify the time right now. So the system boots up. You somehow acquire the real time, perhaps by way of the network time protocol that I'm about to describe, or perhaps you prompt the user for it at boot up or whatever. But you tell the real-time clock what time it is, and then this peripheral will keep track of time elapsed from that starting point that you've either looked up or specified into the very, very, very distant future. And it keeps track of time in units that, in units of like seconds, minutes, years, etc. Right? So it keeps track of like calendar time. So this is an opportunity to talk a little bit about this as well. The way that I'd like to do this is I'd like to start in one of the Pico examples demos. Raspberry Pi has an example that shows how to acquire network time by way of a UDP transaction. And then I'd like to pop over to one of Bruce's examples that takes this Raspberry Pi example and incorporates it into the protothreads infrastructure and uses it to set the real-time clock. I figure we'll start here because there's a little bit less going on, so we can focus specifically on the UDP and network time stuff. So let's do that. This particular example lives in the Pico W directory, Wi-Fi, and then there's a NTP client demo here. And I'll just open this up. In comparison to a lot of the other demos that we've looked at, this demo contains a relatively large number of what look like helper functions, though a handful of these are actually callback functions. We'll talk through each of them, but I propose that let's start here at the top and we'll talk through some of the global stuff and the data structure that we're going to create in order to sort of manage the information associated with this network time protocol. Then we'll pop down to main and essentially follow execution through each of these callback functions and helper functions. It is, in comparison, a little bit of a longer example than many of those that we've looked at, but it's pretty modular, so it's not so hard to parse. So what you'll notice if we look at the top, as perhaps you might expect, we are, of course, including the low-level CYW43 Arch library here. You will see some additional LWIP libraries that we're including. One called DNS. This is the domain name service. I'll show you how we use this in just a moment. But this allows for us to acquire the IP address associated with a domain name, so that if we don't know the specific IP address of some domain name that we'd like to access, we use this service in order to acquire, to have given to us the IP address associated with that domain. pbuff, of course, you'll remember from our last conversation that these pbuffs are the data structures that we use to propagate information up and down through the LWIP stack. So this is where we're actually holding the packet information. And then UDP, because we're going to be doing some UDP transactions here. Okay, and then in order to make things a little bit tidy for us, the next thing that you'll notice is the type def of a struct here with a collection of fields that are relevant for this network time interaction. So these fields include an object of type IP address that's going to hold the IP address of the NTP server to which we connect and from which we receive the real time. As we'll see in a moment, we don't know this IP address at sort of boot up time. We'll use the domain name service to acquire that IP address. You could look up this IP address, I'll just mention. There exist, websites that you can go to find the IP addresses of a whole bunch of these network time servers. You're a good network neighbor if you instead use the domain name service to look up an IP address, and it will give you one. It balances the load among all of these servers, and so it's responsible to look it up instead. There's a Boolean here that we're using to just keep track of whether or not we presently have a domain name service request sent. There's one of these protocol control block structures that we talked about last time. I'll just remind you that these are the data types that we use to manage a network connection, all the information of relevance to a network connection. This is a UDP protocol control block because this particular network connection will be of a UDP variety for communicating with a network time protocol server. There's an object of type absolute time here. This particular example requests the time from the NTP server every so often. This field here is going to hold the absolute time since boot up at which we would like for the next request for time to be received. I think it's like every 30 seconds, right? So we'll set this initially to 30 seconds. I think we set it in microseconds, but okay. And then every time that amount of time has elapsed, we send a request to the server, get the time, and then schedule execution again for that amount of time into the future. And then the alarm here, this is the same kind of alarm that we talked about many moons ago during the, no, we didn't actually talk about the alarms. Yeah, we did, I'm sorry. When we were using the alarm infrastructure to schedule the birdsong synthesis, this is another alarm that we are using to resend a request in the event that it didn't come through, that our previous request didn't come through. Okay, so this is just for our convenience. It's just organizing some information of relevance for doing what we would like to do with this NTP server. You'll then see some macros here with some information of relevance. The server, this is the domain name that we will use DNS to acquire an IP address for. So we'll use that DNS service there to acquire the domain name associated with pool.ntp.org, which I think if you go to this website, you will, actually, let's look. I haven't actually done this, pool.ntp.org. Okay. In any case, I guess there's nothing there to look at per se, but this is where we'll get our IP address. The message length here, this is the size of the packet that we will send to the NTP server and that the NTP server will respond with. This is an NTP specification that these packets are 48 bytes long. A little bit later, I'll talk a bit more about what that packet actually contains. Each byte in there has a specification. We will communicate to port number 123 on the NTP server. This is also a specification. So once we acquire the IP address that we want of the device that we want to communicate with, we will send our packet, our request for time to that server, that IP address at port 123. We'll also receive the packet back from that device at our own port 123, again by NTP specification. The delta here is kind of interesting. That big number, that is the number of seconds between January 1st, 1900 and January 1st, 1970. As it turns out, when you request time from an NTP server, it will tell you the time as measured by the amount of seconds that have elapsed since January 1st, 1900. Yeah, I thought the same thing. It's kind of... Okay, so UTC time, or the Unix standard for time, is measured in seconds since 1970. So this is how we're going to convert between time as reported to us by the NTP server and time as measured by, for instance, our RTC peripheral. By the way, getting ahead of myself just a little bit, when the NTP server actually responds with the time, there's a series of sort of, the timestamps are 32 bits wide. So it will report the number of seconds between January 1st, 1900 and the present moment in seconds using a 32-bit number. Then there's a subsequent 32-bit number that reports fractional time, fractions of seconds, so that you can actually get a measure of time from these devices to better than a second, down to like milliseconds. But it does raise an interesting question. How many seconds can you actually store in 32 bits? I'm alluding to like almost like a Y2K flavored bug opportunity here. As it turns out, there will be an overflow in the year 2036. I think it's January 1st, 2036, I think, or sometime in 2036. So that people are, of course, aware of this impending time. And so there's been a modification to the NTP standard that includes an era field, which tells you which era you're in. Are you in the 1900 era, or are you in the next era that will begin in the year 2036? 2038, okay, whatever it is. There's an impending overflow in the mid to late 2030s. Essentially, the solution to this is that the seconds will be reported in 64 bits instead of 32 bits. Or in other words, there will be information about the era that you're in. We're presently in era 0, which is to say, the first bit in that second 32 bits is 0. In the year 2038, that will enter era 1, which is to say there's a 1 in those top 32 bits. Turns out with those extra 32 bits, the amount of seconds that you can store since January 1st, 1900 leads to an amount of time that is greater than the expected length of the universe, that the amount of time that the universe will last. So that certainly solves that issue. Some other macros here. The test time, I mentioned that we're going to be requesting new information from the server every so often. In fact, it's every 30 seconds. The resend time, in the event that we don't get a response in, looks like 10 seconds, we'll resend a request. But okay, so let's pop down to main, and then we'll sort of follow main through this whole example. So as you can see, we initialize standard I/O so that we can print stuff out. Initialize the CYW43, much like we've seen before. Put the device into station mode, connect to a Wi-Fi network, and then we call this function run NTP test. So let's start there. What happens in run NTP test? First thing we do is call NTP init, which we can just take a look at right here. So when we call NTP init, we allocate some memory to hold a object of that NTP underscore T struct type that we were looking at earlier. So in effect, we create one of these objects, check to see that that's been successful. We then initialize some of the fields of that struct that we created to manage this communication with the NTP server. Oops, what happened? In particular, we set the NTP protocol control block field, and we do so by creating a new UDP protocol control block. And we're specifying that we will allow for communication through that protocol control block from any kind of IP type, IPv4, IPv6, whatever. So we initialize the protocol control block. We then set up a receive callback function for that protocol control block, exactly like we saw in the last lecture. Remember last lecture we were talking about how for receiving UDP packets, you have to set up a receive callback function so that you know the system knows what to do with information that it receives. Here we are setting up a similar receive callback function. The function that's actually going to be calling back is this NTP receive, which we'll talk about here in a moment. But this is the function that will be called back. Okay, so we initialize this whole thing. Then we enter this while true loop, and we see whether it is the case. We check two conditions. The first condition is it time for us to do another NTP request? And we do that by comparing the present time, measured in microseconds since boot, against the NTP test time field of that struct, which you'll recall is holding the next time at which we should request more network time information, right? So we're seeing, is it time yet for us to do this? In the event that it is, we may carry on, but not before we check the second condition, which is whether or not we presently have an active domain name service request out, in which case just wait because we've already done this. Okay. But in the event these conditions are true, we set the resend alarm field of our NTP struct we initialize an alarm associated with it. What we're specifying here is that in the resend amount of time, which you'll recall from up above is 10 seconds, if in 10 seconds we haven't canceled this alarm, then please call the NTP failed handler function, another function that lives further up that we'll look at in just a moment. And when you call it with the following two arguments. Okay, so we're setting up essentially a fail-safe here. So in the event that we don't hear anything back, this alarm will fire and will take some action. But in the event that we do hear something back, as we'll see, we end up canceling this alarm. Okay, so this is just us setting up a fail-safe. We're going to do some lower level LWIP stuff in our application code. We have this system set up running in thread-safe background mode, which you may recall from last lecture. That means that there is a background interrupt running occasionally that is doing some management of the Wi-Fi chip. We do not want for that process to interrupt our process while we are working with LWIP stuff. So these two functions, CYW43 arch LWIP begin and end, those set up a LWIP critical section. So that says this function that we're calling here will not be interrupted by that background process that's doing occasional tending of the Wi-Fi hardware. So we can be absolutely confident here that we're not going to be interrupted. Prevents any sort of dangerous situations where we're modifying something, then we get interrupted, and we're in a non-stable configuration, right, during that interrupt. Okay, but what do we actually do? We're calling a function called DNS get host by name. Does exactly what the name sort of suggests. It, as an argument, it takes a domain name. NTP server, you'll recall from up there, is that pool.ntp.org website name. And it will provide us an IP address. This function takes as a second argument the address of the place in memory in which to store the IP address that we get back. We're going to store it in the NTP server address field of that NTP struct. And then there's some fields here just to indicate status, DNS found and state. So in any case, this function here is taking as an argument the URL of the domain for which we would like an IP address. We get that IP address back, and we'll store it in that field of that struct. Having done that, we set the DNS request sent field of our struct to true, just to keep track of, to remember the fact that we've got the domain name. Okay, so that's what we're using to keep track of that fact. In the event that that all went okay, right? So this returns an error code status. In the event that the error code says no errors, error okay, then we call this next function that we'll take a look at here in just a moment, which is NTP request. Questions so far? So at this point, all that we've really done is initialize the protocol control block and acquired the IP address associated with the URL that we're interested in. Okay, so then let's take a look at this NTP request function here. Here it is. This is where we actually send a UDP packet to that server. So now we know the IP address of the server. We know that we want to communicate with that server through port 123 by NTP standard. Now we actually have to send it something so that it can respond. So what are we going to send it? Well, we're going to allocate a pbuff here. This is, again, this is the data structure that we use to hold our packet information in the LWIP infrastructure. Okay. We specify that it's going to be a transport pbuff. It's going to be this long NTP message length. You'll remember that's 48 bytes. It's a pbuff RAM. That is to say, this is being allocated from RAM, from the specific section of RAM that we have given to LWIP. Right? So it's going to allocate a pbuff here. For our own convenience, we're declaring a pointer to an unsigned int that points to the same place in memory as the payload field of that pbuff. So if we dereference REQ there, then what we're in fact doing is setting the payload field of this pbuff. We zero out the payload with a memset. So we say, please go to this memory address, and for this many bytes, set all those bytes to 0. Just clear it. We set the first byte of the payload to 0x1b. And in fact, that is the only byte that we set to something that is non-zero. As it turns out, that's all that we actually have to set in order to get time back from a NTP server. What this actually means, if you look at the standard for what each byte in this packet represents, one of these represents the mode. In effect, we're telling the NTP server that we are playing the role of the client. And so when it receives this, it looks at that particular byte and says, ah, I have received a message from a client. The other one, I wrote it down, I can't remember. The other one is, I can't remember. You look it up. We're essentially just modifying 2 pieces of information in that first byte. That's all that we have to do to tell the NTP server, please respond to me with the time. Okay, and then we send that pbuff off. We send that UDP packet off by way of a UDP send to call. Here's the protocol control block through which we're sending the packet. Here's the pbuff. Here's the address to which we're sending the packet, which we got from the domain name service. And there's the port to which we're going to send. Off it goes. We free the payload. We end this critical section. And now our packet is in flight, right? So our application code now, it has sent off a request for the time, and now all that it's going to do is sit and wait for a response. Now you'll remember down here where we set up the initialization, is this where we did it? Yes, it is. You'll remember that when we set up the initialization for this protocol control block, we associated a receive callback function with it, right? So we've sent off a packet saying, please tell me what time it is. We will receive that information back by way of a UDP packet sent to our port 123. This says, hey, when a packet comes back to this protocol control block, please send it to this receive callback function. So when we get a response from that server, this function is going to be called with a pbuff that holds the packet information from that NTP server. So let's go look at that receive callback function. It's right here. So this gets called with the same arguments that we saw in our last conversation, because this is the same kind of infrastructure that we were looking at last time in our conversation about UDP send and receive. And what do we actually do here? We are accessing a couple of specific bytes within the pbuff payload that we received back. In particular, we're accessing byte 0 ANDed with 0x7, so some specific bits within byte 0, which if you look at the specification, those particular bits within the first byte represent the mode for that particular UDP packet. When we sent a packet off to the server, we set these bits to a value that represented a mode of client. It says this is a packet from a client. We should expect to receive a packet back with the mode indicator there having a value that indicates server. I'm a server. We're going to verify that, okay? But that's why we're parsing that out. Stratum here, you can see that we're accessing byte 1, not 0, but byte 1 of the received payload. The stratum is a field that indicates, if I recall correctly, it indicates whether the particular NTP server with which we're communicating is a primary time source. That is to say, it knows what time it is from some sort of a primary resource, like for instance GPS, something that's actually giving it the time, or if instead it's a secondary time resource. It's communicating with another device that has a primary time resource. The reason that we're parsing that out is that is also the field that will indicate an error. And so if we observe that there is a, if we observe that the stratum field is 0, that indicates that there was an error and we should ignore that packet. Okay, so that's why we're parsing it out. And then we check some of this stuff that we just parsed out. We confirm that the IP address of the UDP packet that we just received is the NTP server address to which we sent our request. We received the packet back from the same IP address that we sent a request to. We furthermore check that we received that packet through our own port 123, because that's where NTP packets come to, port 123. We check that the total length of the payload of this packet is 48 bytes, because that is how long NTP packets are. We check that the mode is 4, because that indicates that this came from a server. And we check that the stratum field is non-zero, because that indicates that there was no error. If all that is correct, then we know this must be the response from the NTP server with which we were just communicating. And now we can parse it out and get the time. So we do this. It takes just a little bit of footwork because of big endian, little endian disagreement. NTP server is responding in one of the two, and we're keeping track of time in the other of the two. So that's why you see some of these shift modifications here. But in short, what we're doing here is creating a size 4 array of bytes initialized to 0. And then we're making use of an LWIP helper function here called pbuff copy partial. This allows for us, as the name suggests, to copy part of a pbuff payload, not the whole thing. And we're saying, please go to the pbuff payload P here, with which this function was called. The destination in which I would like for you to place the data that you copy is this array that we've just created called seconds buff. I'd like for you to copy this many bytes, the size of seconds buff, and please start copying from byte number 40 of the received packet. Turns out that when these NTP servers respond to us, they respond with a few different timestamps. They respond with a reference timestamp that indicates the time at which they last updated their time, to my understanding. They respond with a second timestamp, which indicates the time at which they transmitted the packet back. There's another field in which we could, if we wanted to, in the packet that we sent, we could populate the timestamp, the time at which we sent the request to the client, or to the server rather. We aren't actually doing that, though we could. And then the last one is the time at which the server received our request. And so it's responding with, here's what time I received your request, here's what time I sent a packet back to you, a response back to you. We may optionally have included in our transmission to it, which it will send back to us, the time at which we sent the packet. As you could imagine, this is providing sufficient information for us to calibrate out the time that it takes for the data to move from us to the server and back to us, which maybe you care about or maybe you don't, right? For many of our applications, probably you don't, but perhaps you do. And in the event that you do want to actually measure the flight time of these packets, there's sufficient information there for you to actually do that. Okay. So then we populate a unsigned int here with the number of seconds that have passed since 1900. This is the measure of time reported to us by the NTP server. We do that by just big endian, little endian, the information that we received back from it. Okay. But this is just some big number that represents a number of seconds. We take that number of seconds and subtract off that NTP delta number, that big number up there that represents the number of seconds between January 1st, 1900 and January 1st, 1970. That gives us the amount of seconds since 1970. And as we'll see when we pop over to Bruce's augmentation of this code, with that number, we could then set the real-time clock. The real-time clock peripheral on the RP2040. Okay, so supposing all this goes well, the next thing that happens is that we would call this NTP result function, which lives where? Somewhere up here. The NTP result function, we call it with that number of seconds. And what you can see is this function creates an object of type, a pointer to an object of type TM, which we're calling UTC. And then we call this, this high-level convenience function offered by the SDK called GM time, which will take that number of seconds and convert it to months, days, years, etc. Right? So we give it a big old number of seconds. This function, a convenience function, will then populate the fields of this TM object. Fields includes things like day, month, year, hour, minute, second, etc. It'll populate all of that for us based on the number of seconds since 1970. As you might expect, it's with an object of that type which we could then set the real-time clock. Any questions about this? How old were folks during the Y2K bug? -years old. Okay, yeah. Do you have memories of that, Bruce? The nature of the bug that people were worried about, to my knowledge, was essentially a data type problem, where it was the case that there were programs that had been written, years or decades ago. They used a data type with a certain amount of bits to hold the year information. And once the year passed 1900, basically it was holding year information using 2 digits worth of information, if I recall, 98, 99, etc. The question was, how well does this software respond to the year suddenly becoming 0 in this data type, basically with that overflow occurring? And it will think suddenly that it's in the year 0, whatever the hell that means to that system. And the worry was that the consequence for some of these systems might be that they break in hard to predict or perhaps dangerous ways. It turned out, to my knowledge, not to be. A few systems freaked out a little bit, but it was generally okay, to my knowledge. Okay. So it was because of a lot of work that this, yeah. Okay. Any questions before I pop over to like I said, a demo that is this consolidated into protothreads infrastructure, so you can incorporate it into your projects a little bit more elegantly, perhaps, and it involves some real-time clock stuff. Okay. So this is this is one of Bruce's web pages, which I will just remind you, you can find by going to Bruce's website, RP2040 projects, and then if we scroll down here a bit, there's a page on network time protocol and the onboard real-time clock, which includes an example here that uses NTP to get the time and then uses that time to set the real-time clock. So let's just take a look at this. And what you will observe is that a lot of the stuff here is quite familiar. It looks pretty much like we were just looking at. And in fact, many of these helper functions are unchanged. What has changed, if we scroll down just a bit, is down in main, rather than just calling whatever we called last time, that function that got the whole system going, what we do in thread instead is schedule a bunch of threads. One of these is a serial thread through which the user can ask for the time, for instance, or request that the time be updated, for instance. 2 of these are just threads that are toggling LEDs to test multitasking stuff. And then there's one here called protothread NTP, and it's in this protothread that much of that that stuff that we were discussing ends up getting consolidated. So if we look at the protothreads NTP thread, you will observe that this looks very familiar to that function that we were just looking at. It's just wrapped up in this thread. You'll notice furthermore that this thread stalls on a semaphore so that we can tell it to go run and request a new time from the NTP server at the user's request. So if by the serial interface the user says, get me the time again, click, signal the semaphore, and then that whole procedure that we just talked through then occurs. So that procedure is largely the same, except when we finally get the result back, some additional stuff happens. Well, let me start up here, actually. One of the other differences that you'll observe is there's some additional libraries pulled in here. In particular, there's one called hardware RTC. That's the real-time clock hardware API. Okay, so we're pulling that in because we're going to be interacting with the real-time clock. And then there's also a library from the util directory of the Pico SDK called datetime. This is so that we can pull in a handy struct, a handy data type for interacting with the real-time clock. That struct having the name datetime. Its fields represent the date and the time. It has a year field, month, day, day of the week, hour, minutes, and seconds. And so after having gone through largely the same sequence of events that we just described, right, you'll remember that that sequence of events ended up with us up here at the NTP result function. In the previous example that we were looking at, all that happened was the date and time were printed out. Some additional stuff is now happening. So you can observe that as before, we're using this GM time convenience function to take the number of seconds since 1970 and converting that to, you know, year, month, day, et cetera, et cetera, et cetera, all these fields. And then furthermore, we are calling we are setting the fields of this date time struct, globally declared here someplace, this one here, right? We're setting the fields of this date time struct with the name t for time, with the stuff that we just, with the fields that we just got from this GM time convenience function. So for instance, we're setting the year to the year that we just got, plus 1900. The month to the month plus 1. Why are these offsets here, actually, Bruce? I can't remember. Okay, sure. And then we set the other fields, of course, the day field, the day of the week field, the hour, the minute, the second. And then finally, we call a function from the RTC hardware API called RTC set date time. And we pass as an argument to that function a pointer to this date time object that has all these fields. And that sets the real-time clock. And then once the real-time clock is set, it is just going to keep track of time elapsed. So it will just be in the background incrementing the second field every second. Once it gets 60 of those, it'll increment the minutes fields and so on and so on and so on. And it will run for months and years or whatever. It'll just keep track of time. And then, as you might expect, within the hardware API for the real-time clock, there exist functions that allow for you to like read the time. Tell me what year it is. Tell me what month it is, etc. Right? So this, once you've set the real time once, it then manages that real time for you into the future.
Do you know the drift of the RCC on top of your head?
2.56 seconds a day. Yeah. 15 minutes a year, which suggests that perhaps every now and then you want to go ping that NTP server again to update your time, right? How often? I don't know. It depends how accurately you need to.
Well, also human uptime in a year.
Sure. Sure. Any questions about this? So I think this is neat because it's a tremendous capability to be able to actually access the real time from one of these little devices. If you get on the network by way of the procedure that we talked about earlier with the Pico W, then with only UDP communication infrastructure, you can get that time. Handy for watches. Handy also for, like, you know, if you are gathering data of any variety, it's probably the case that you want to timestamp the data. And without access to real time, you can, of course, timestamp it with time elapsed since boot up. And perhaps it's the case that you've, you know, written down the time at which you booted the system up. But if your device, your data gathering device, has access to a Wi-Fi network, this is sort of an autonomous way by which you can get the real time with which you could timestamp data for, you know, scientific or diagnostic purposes. There is a field for leap seconds. And so one of the, and in fact, I believe it's the first bit or couple of bits of the packet that we get back from the NTP server, it will indicate whether the previous minute was 59 seconds or 61 seconds in the event that there was a leap event that occurred. And so it allows for you to manage leap years. Okay, I'm about out of time. So I will be in lab this afternoon. I'll see many of you then. I'll see the rest of you either tomorrow or Friday.